At 6 seconds past 8:30 on Thursday morning, the ground moved under the Oakland Zoo. The zoo sits directly on the Hayward Fault. Staff there reported no damage, but video recorded on the grounds caught the animals reacting, vocalizing, which is the word for the sounds animals make to warn each other. The zoo's chief executive, Nick DeHaja, noted that animals can feel low-frequency vibrations in ways humans cannot. 2.5 miles north of San Leandro, 5.2 kilometers down, magnitude 3.8. Thousands of people filed felt reports with the USGS from Santa Rosa in the north to Santa Cruz in the south and out to Sacramento. Office workers in downtown San Leandro felt their building sway and went outside. A water main let go on Decoto Road in Fremont and put a geyser into the street for about 20 minutes. BART slowed every train in the system while crews walked the track. And at 3.7 seconds after the rupture began, ShakeAlert issued its first message. Nobody was hurt, nothing collapsed. By 9 o'clock, most people had gone back to their morning. Now, the title of this video says California's earthquake map has changed. That is true. It is genuinely true, and it is one of the more important pieces of earth science published this year. But it did not change on Thursday. It changed in April on a supercomputer in a paper that almost nobody outside the field read. And what it found is stranger and more specific than the shaking will be worse. It is a finding about where the shaking goes, and it turns on a variable that nobody can know in advance. So there are two questions today, and I am going to answer both properly. First, does a magnitude 3.8 on the Hayward Fault mean the big one is closer? And second, what actually changed on that map and why? No guessing, no dramatizing, just the numbers, the mechanism, and the stakes. Before we start, if you are in the East Bay, tell me in the comments where you were and whether you felt it, because half the Bay Area apparently did, and the other half slept through it. Subscribe if you want the plain version of these, and a thumbs up helps. Let us go for 5,000. Now, let us get into it. First, Thursday precisely. The USGS logged the event at 8:30 minutes 06 seconds in the morning, Pacific time, on the 13th of August. Epicenter, 37.759 degrees north, 122.151 west, near the Oakland Zoo and Bishop O'Dowd High School. Depth, 5.2 kilometers. Catalog number, NC75417557. The magnitude was first reported as 4.1, then revised to 3.9, then settled at 3.8. That revision sequence is worth 30 seconds because people read it as agencies backpedaling, and it is the opposite. The first number comes from an automatic solution using the earliest arrivals at whichever stations report fastest, designed for speed, not precision. As more stations report and a human analyst reviews the waveforms, the estimate tightens. Downward revisions are common because early amplitude-based methods tend to overshoot on the first few seconds of data. Two aftershocks followed at 7 minutes past 9, a magnitude 3.0 and a magnitude 2.8, 4 seconds apart in the same spot. And here is the detail that changes how you should read the whole event. The main shock was centered on a minor fault strand, not on the main trace of the Hayward Fault, which is why seismologists did not treat it as a sign of the larger structure waking up. Dr. Angie Lux, a project scientist for earthquake early warning at the Berkeley Seismology Lab, put it about as plainly as it can be put. This is not something unexpected for the Bay Area. It does not mean we are going to have a big earthquake soon, but we do know we are overdue for a large earthquake on the Hayward Fault. Both halves of that sentence are true, and most coverage only carries one of them. Now the fault itself. The Hayward runs about 74 miles, 119 kilometers, from San Pablo Bay in the north down to Fremont. It is a right lateral strike-slip fault, meaning the two sides grind horizontally past each other. And if you stand on one side and look across, the far side moves to your right. Its problem is not its size. It is its address. The Hayward runs directly beneath the most densely built part of the East Bay: Oakland, Berkeley, Hayward, Fremont, San Leandro. Not near them, through them. It last produced a major earthquake in 1868. That is 158 years ago, against a historical recurrence interval of roughly 140 years. And the USGS assessment is that there is about a 1 in 3 chance of a magnitude 6.7 or greater on the Hayward within the next 30 years. Right. Overdue. I want to handle that word carefully because it does more damage than almost any other term in this field. A recurrence interval is a statistical average derived from paleoseismic evidence, trenching across the fault, dating the sediment layers that were offset by past ruptures, and working out roughly when each one happened. If 5 ruptures show up across 700 years, you get an average of about 140. But an average is not a schedule. The individual intervals in that record vary, and a fault has no mechanism for knowing how long it has been. It does not accumulate impatience. It accumulates strain. And it fails when the stress on the fault plane exceeds the friction holding it shut, which depends on the local strength of the rock, the fluid pressure in it, and the stress transferred by every other earthquake in the region since the last one. Overdue means the strain has accumulated to levels consistent with past major ruptures. It does not mean next Tuesday, and it does not mean the probability rises measurably from one week to the next. So, did Thursday move the needle? No. A magnitude 3.8 on a minor strand releases a trivial fraction of the energy stored on a fault capable of a magnitude 7. The scale is logarithmic. Each whole step up is roughly 32 times the energy, which puts a 3.8 something like 100,000 times smaller than a magnitude 7. It drained nothing. Which brings us to what actually did change. In April of this year, scientists at Lawrence Livermore National Laboratory and Lawrence Berkeley National Laboratory published a study in Seismological Research Letters. The lead author is LLNL seismologist Arben Pitarka. His co-authors include the mathematicians Anders Peterson and Bjorn Sjogren, and structural engineer David McCallan of the University of California Office of the President and Berkeley Lab. What they did was run 50 separate magnitude 7 earthquake scenarios on the Hayward Fault using the Department of Energy's exascale computing infrastructure, the most powerful class of supercomputer that exists. 50 runs, not one, because they varied the things nobody can predict: how much the fault slips, where the rupture starts, and how fast it propagates. And the headline finding in Pitarka's team's own reporting is that some areas near the fault could experience ground shaking up to 50% stronger than prior models anticipated. That matters because building codes, retrofit requirements, and infrastructure design standards are calibrated against ground motion estimates. If the estimates are low, structures engineered for a certain level of force meet something else when the real earthquake arrives. But the number is not the interesting part. Why it is 50% stronger and where is the interesting part. And this is the piece almost every write-up leaves out. The mechanism is called rupture directivity. Here is the thing people get wrong about earthquakes. A fault does not break all at once. The rupture starts at a point, the hypocentre, and then tears along the fault plane at something like 2 to 3 kilometers a second. A magnitude 7 rupture on the Hayward might run for 50 or 60 kilometers, and that takes time. 15, 20 seconds. Now think about what that means for the waves. Every point along the fault radiates seismic energy as it breaks. If the rupture is running toward you, Each successive burst of energy is released from a point closer to you than the last one, so each wave has less distance to travel and they arrive bunched together. It is the same geometry as a Doppler shift, or the way a sonic boom stacks pressure waves in front of an aircraft. The energy from the entire rupture arrives compressed into a short, violent pulse. If the rupture is running away from you, the opposite happens. The waves are spread out over a longer time, and what you feel is weaker and more drawn out, even at exactly the same distance from the fault. Pitarka's team describes the affected region as a cone-shaped zone that starts at the epicenter and spreads out along both sides of the fault. Inside that cone, the ground motion is pulse-like and, in the study's own language, far more intense than normal. Same magnitude, same fault, same distance. Radically different shaking, decided by which way the tear happened to run. And there is a second effect stacked on top, which is about what the region is made of rather than how the fault breaks. The Bay Area is not uniform rock. It is a set of sedimentary basins, Livermore Valley, the Santa Clara Valley, the Bay margins, sitting in harder bedrock. When a seismic wave passes from stiff rock into soft sediment, it slows down, and as it slows, its amplitude grows because the energy has to go somewhere. Worse, the basin edges reflect waves back inward. Energy that enters a basin can bounce between its walls rather than passing through, so the shaking is not only stronger, but lasts substantially longer. The LLNL team's phrasing is that the region's geography will shape the next big one, trapping seismic waves in basins like Livermore Valley and amplifying the destructive energy. Now put those two things together, because this is where it becomes an engineering problem rather than a geology one. Directivity pulses and basin resonance both push energy toward the long period end of the spectrum, slower rolling motion rather than sharp high-frequency jolts. Every structure has a natural period at which it prefers to sway. For a stiff two-story house, it is a fraction of a second. For a tall building or a long-span bridge, it can be several seconds. When the period of the ground motion matches the natural period of the structure, the building absorbs energy efficiently and the sway builds with each cycle. Which is why the study flags this shaking as especially dangerous for tall or flexible buildings, the towers, the bridges, the elevated structures. Not the ones most people picture when they imagine earthquake damage. Before I answer the question, one thing about those animals at the zoo. You will see the vocalizing described as animals sensing an earthquake before it happens. They did not. What they detected was the earthquake itself, slightly earlier than the humans standing next to them. Every earthquake sends out fast P waves ahead of the slower, damaging S waves. Animals with better sensitivity to low-frequency vibration, and with their ears closer to the ground, register the P wave arrival that a person may not consciously notice. That is not prediction. It is the same event detected a second or two sooner. ShakeAlert does exactly the same thing, deliberately with instruments. 3.7 seconds after that rupture began, it had already issued its first message. There is one more property of the Hayward worth knowing because it makes this fault unusual and it is visible from the pavement. Parts of the Hayward creep. The two sides slide past each other slowly and continuously, a few millimeters a year, without earthquakes. And because the fault runs straight through built-up neighborhoods, you can go and look at the result. Curbs offset, walls sheared, pavement cracked in a line that runs on across the next street and the next. There is a stadium at UC Berkeley that sits astride the fault and has been slowly pulled apart by it. Creep matters for two opposite reasons, and the honest answer is that seismologists have argued about it for decades. On one hand, a creeping section is releasing strain harmlessly. The fault is unloading itself a little at a time, so there is less stored energy available for a rupture. On the other, creep is usually confined to the shallowest few kilometers. Below that, the fault is still locked, still accumulating. and a creeping upper section can act as a lid on the loaded rock beneath it rather than a relief valve for it. So the Hayward gives you a fault that is measurably moving in public in a way you can photograph, while the part that matters stays shut. That is a strange thing to live on top of, and it is one reason this fault has been instrumented and studied as intensively as any on Earth. Right, let us answer the question in the title. Is the big one getting closer? Yes, at precisely the rate it was getting closer last week and the week before that. The Hayward accumulates strain continuously because the Pacific and North American plates never stop moving. Nothing on Thursday accelerated that, and nothing decelerated it. The fault does not know what day it is. But the map genuinely did change, and here is what actually changed on it. Before this study, seismic hazard for the Bay Area was largely expressed the way hazard is usually expressed, as a value attached to a location. This much expected ground acceleration at this spot for a design basis earthquake. A number you could look up for an address and hand to an engineer. What 50 exascale simulations show is that hazard on the Hayward is not a number attached to a place. It is a pattern, and the pattern is set by variables that cannot be known until the rupture is already happening. Where the rupture starts, which direction it runs, how fast it propagates, whether your neighborhood sits inside the directivity cone or outside it, whether the waves that reach you have been amplified and trapped by the basin under your feet or pass through bedrock. Change the hypocentre by a few kilometers and the map of who gets the pulse redraws itself. That is why they ran 50 scenarios instead of one. Not to find the worst case, but because a single scenario would have been a description of one possible earthquake rather than a description of the hazard. And it means the honest version of the finding is not everything is 50% worse. It is that some areas near the fault in some rupture geometries get shaking up to 50% above what the models assumed. And which areas those are depends on a coin flip that has not been tossed yet. That is a harder thing to build a code around than a single number. It is also considerably closer to the truth, and the only reason we know it is that somebody was finally able to compute 50 full physics simulations of an earthquake that has not happened. The map changed in a paper in April. Thursday was just the ground clearing its throat. So, what do you actually do? Find out what you are standing on, not just how far you are from the fault. Distance is not the whole story. Basin sediment and the directivity cone both matter. California's Alquist-Priolo earthquake fault zone maps are public, and the USGS publishes hazard mapping you can look up for an address. Find out whether your building has been retrofitted, especially if it is a soft-story structure, an apartment building with an open ground floor for parking or shops. Those are among the most dangerous buildings in an earthquake. Many cities have retrofit ordinances, and compliance is not universal. Renters in particular often have no idea of the seismic status of the building they sleep in. Turn on earthquake alerts. ShakeAlert fired 3.7 seconds after Thursday's rupture. For a distant event, that is enough time to get under a table, and falling objects cause an enormous share of injuries. And do the boring things. Water for 3 days per person, medication, a torch and a battery radio, shoes under the bed, cash in small notes because card terminals need power, one out-of-area phone number the whole family calls. It is an afternoon of work. The Hayward fault has been doing this for millions of years. It built the hills that Oakland and Berkeley are draped across. The ridge line that the university sits on exists because that fault has been lifting it, one rupture at a time, for longer than there have been people to notice. Thursday's earthquake was 100,000 times too small to matter. The paper in April did not move the fault a millimeter. But one of those two things told us something we did not know before, and it was not the one that shook the windows. Tell me in the comments where you were on Thursday. Subscribe if you want the plain version of these, and thank you for giving me this much of your afternoon. I will see you next time.